use the same techniques that we use for calculating proportions, right? Estimates for proportions, right? Intervals, confidence intervals in particular. We are going to do in this section, estimating a single mean from a sample without using salt. So we're going to do it by calculation, essentially. And we're going to use a guy called the empirical rule. So let's just remind you how the empirical rule works. If you want, oops, let's do them in order. If you want a 68% confidence interval, then you take the mean and you add and subtract 1 standard deviation. You remember the empirical rule is also called the 68, 95, 99.7 rule, which I actually like that rule better. If you move up and you want to do a 95% confidence interval, then you will take the mean and you will add and subtract how many standard deviations for a 95%? Correct, 2 standard deviations. And last but not least, rather awkward number, but if you want 99.7% confidence interval, then you will take the mean and you will add and subtract 3 standard deviations. Are we all comfortable with the empirical rule? That's what it essentially says. Now, in this world, we are going to have a sample. And so the sample is going to be size n. So let's suppose I collect a sample of 100 people. And the mean of my sample is going to be called x bar. And let's say the answer ends up being £150, right? So I randomly selected 100 adults and their mean weight was £150. So far, so good. Now, if I was trying to estimate the average weight of, well, let's say the population is Bremerton, right? So these people are all in Bremerton. Then the average weight of an adult in Bremerton, I could just say it's £150. That would be my best guess based on my sample mean, right? That's the sample mean, right? Probably put the word sample in front of it. But we'd like to do better than that. We would like to do a confidence interval, right? One of these 3. So we could say, look, we're 95% confident that the real average is in this range, right? The real mean weight is in this range, or 99.7 would be a good one as well, right? So we are going to use that same trick as before. It's called the sampling distribution. And in the sampling distribution, the mean is going to be x bar. And the standard deviation is called the standard error. And the standard error is, well, here's the formula for it. It's not got the square root of p and 1 minus p and all that stuff. It's a different formula. It's little s divided by the square root of n, where n is the sample size and little s is the standard deviation of the sample. So can you imagine every one of these 100 people, right, was put into, you know, your software or your calculator, and you found the standard deviation of them, right? So little s, looks like a 5, right? Little s is the standard deviation of the sample. And these guys will allow me to get a 68, a 95, or a 99.7. And we'll show you later how we use these 2 guys. But right now, we're just going to find the standard error part, right? Okay. So the standard error is S over the square of n, right? So can I find one? Okay, suppose the sample was 39 and S was 5. Then in that situation, the standard error would be 5 over the square root of 39. Keep meaning to change my values on this, but I never do. 5 divided by the square root of 39. And that ends up being 0.8000, right? 6. Let's suppose they wanted the answer to 2 decimal places. It would be 0.80. Would you agree calculating the standard error is a lot less messy than doing it when it was a proportion? Isn't it just S divided by the square root of n? Any questions about that so far? As long as they tell me the sample size and you tell me the standard deviation of the sample, that's these two guys, can I get the standard error by taking this guy and dividing by the square root of that guy? That's really the only two numbers in town. And what this is measuring is how spread out you would expect the standard deviation to be if you did this sample of 39 lots and lots of times. So question 2 is asking us to find the standard error in a number of situations. So in question A, they told us the mean height. Well, they didn't actually tell it. Oh, they do. They tell us the mean height. They tell us the sample size. And they tell us the standard deviation. Now, if they wanted to know what the mean is, wouldn't the answer just be that guy? It's not really a question. And if they asked us to find the standard error, it would be this formula, which is what? 3.9 divided by the square root of 99. So 3.9 divided by the square root of 99. And to 2 decimal places, that's 0.39. We good with that? I just had a look. They wanted the answer to 1 decimal place. Have you ever done that? You write the answer to 2 and Web Assigned says you're wrong because they wanted it to 1. Now that I looked at the question, that's the answer to 1 decimal place. That's what I should do. You might say, these are 2 different questions. If all you wanted is standard error, you don't need to know what the mean is. Would you agree it's irrelevant what the mean is? Because the standard error only uses these 2 guys, right? It doesn't care what the mean is. Let's move on to 3. In question 3, it says, suppose that a random sample of 81 men, and they measured how long their feet were, and the average that they got was 27.5 centimeters, and that the standard deviation was 3 centimeters. And it says, calculate the standard error. So it's going to be S over the square root of 9, 3 over square root of 81, 3 over 9, to 2 decimal places, 0.33. And then they finish with this weird sentence, because that's part A, and that's the answer to part A. In question B, they write this down. Over all possible samples of n equals 81 from this population, the average difference between the sample mean which in our case was this number, and the population mean, which is, you know, that mysterious number that we're trying to do, it is about. Have you ever had one of those questions where the question looks extremely difficult and the answer is kind of weird? That sentence is giving us a definition of what the standard error is measuring. It's measuring how spread out the samples are, right? If you take lots and lots of samples, right, you get different values each time, right? So if you did a sample of size 81 lots and lots of time, what's the average amount you would expect? You would expect the average to be about 0.33. And they're not talking about the mean, they're talking about the average spread, right? How much it spreads about. So if you ever see a sentence that looks something essentially like that, your answer will be the same answer as the standard error that you've already found. Like, you ever had those things where they say, for instance, someone gave me a question about, what was it? The point estimate for the proportion. Did you remember a question that said that? And it just ended up being another name for p hat. That's kind of what that one looks like. So if I gave you a random sample size and I told you what the standard deviation was, are you comfortable about evaluating and finding that guy? Do you feel comfortable about doing that? So if I told you this guy and I told you this guy, could you find the standard error of the mean? Right? S over square root of n, 3.7 over the square root of 120. Let's say this time it's to 2 decimal places. 3.7 divided by the square root of 120, and to 2 decimal places, 0.34. If the question tells you that the mean was 103.712, does that change anything as far as the standard error is concerned? Is the standard error still going to be this number if I tell you the mean is that? What do you think? Is the standard error still going to be that number if I add an extra piece of information, which is the mean?
Yes.
Yeah.
No effect. Not going to change it a darn thing. Because doesn't this formula not use X bar? So I don't care if X bar is 20 or 2 or 4 billion. The standard error doesn't use it. It doesn't care what it is. It only uses how big is your sample and what was the standard deviation of your sample, right? How spread out it was. Are we good? Right. Because I'm just looking at quite a few questions that tell me this number, but I don't even use it in my calculation, right? They tell you this stuff, but they only ask you for that. And sometimes when you see a number, there's a temptation to say, well, they wouldn't have told me that if it hadn't to be used somewhere. And the answer is yes, they told you that, and it's never used anywhere. So let's create a confidence interval like I promised at the start. Right, one of those.
Will you be doing number 5? Because I believe there was a similar question on our actual test that looks like number 5, and I didn't completely understand it.
Okay, well, let's go for it. This is the one you got would be I hope a proportion version of this, but it is a pretty standard question. In question 5, suppose you're interested in estimating the average number of miles per gallon that your car can get, right? So you calculate the miles per gallon for each of the next 23 times you fill the tank, right? So you know you hit your what's it called? Your tachometer, right? The little button that resets to 0, right? And you fill up your tank, and then when it's pretty much empty, you write down how many miles it's done. So that's how they came up with the answer. And this particular person did it 23 times. So you've basically told me that your sample is 23. And we are making an assumption that I haven't mentioned yet, and this is that the data that I'm getting comes from bell-shaped, right? It's nothing weird. It's not skewed left, skewed right, right? It has that shape to it. We're making that assumption for every question. And what is it? And the mean that we got was 30 miles per gallon. Pretty cool. And we want to use our empirical rule to find a 68, a 95, and then a 99.7 confidence interval. And there's one other number which I'm trying to find because I know it's here somewhere. And here we are. And the standard deviation we were told was 1 mile. So with only those 3 data points, we can now generate a 68, a 95, and a 97. Let me show you what the formula looks like. Right. Let's do a 68% one. It's going to be the mean, which I'm going to write like that, plus or 1. Now, see when it says standard deviation, we are going to do plus or 1 standard error. For a 95% confidence interval, it's going to be the mean of our sample plus or minus 2 standard errors. And for the last one, which is a 99.7% confidence interval, we're going to take the mean and add and subtract 3 standard errors. So I need one more number, and I need to know the standard error. And it's S over the square root of n. It's 1 over the square root of 23. So the number I'm going to use for the standard error, they want 3 decimal places, so I'm going to do this to 4. 1 divided by the square root of 23. And to 4 decimal places, it's 0.2085. If you want your answers to be to 3 decimal places, then make sure everything else is to more accurate, right? So I'm doing this 4, maybe 5, even if I felt it was necessary. So this guy is going to be the mean, which is 30, plus or minus 1 standard error. So that's going to be 27.915 to, let me do that again, 29.7915 to 30.2085. And now I'll round it off to, what did they want? I've lost the question here. Number 5, they wanted it to be to 3. So they're going to do 791. I'd argue about the 1 being a 2, but never mind. 3.2085 9. Right. I'd say that was a 2, but evidently they're saying it's a 1, so I don't know. You have to live with that inconsistency. Because technically, shouldn't you always round up when it's a 5 and round down when it's a 4? That's how I was taught to round off at least. Now you want this one. It's 30 plus or minus 2 of these guys. So it's going to be 30 plus or minus that guy. And that's going to get me 29.583 to 30.417. And this time, we agree. Go figure. So one more. This is going to be the mean, which again is 30, plus or minus 3 standard errors. So it's going to be 30 plus or minus, do that on the calculator, I think. And the answer we get here is 0.6255. If you take this away, you will get 29.3745. And if you add it, you're going to get 30.6255. If we round it off to the 3 that they want, we're going to disagree on this side, but we're going to agree on that side. Go figure. So, word of warning, if this guy here is a 5, WebAssign isn't very good at the early ones, right? It seems to round off differently. It seems to be okay on one side, but it rounds off slightly weirdly on the other side, which might be something to do with its programming. So let's interpret that. If we were this guy in his car, wouldn't we be 68% sure that the mileage he typically gets is somewhere in that range? I'm 95% sure it's somewhere in that range. And I'm pretty much certain, right, 99.7, pretty much guaranteed, that isn't the answer somewhere in that range. Would you agree that that's quite a narrow range of values? So if he was talking to someone and he says, what does your car get? He's going to say, oh, somewhere between about 29 and 31, right? You probably wouldn't give all these decimals. So we know within, what, 99.7% sure, right? Not 100% sure, but pretty much sure. That isn't the answer somewhere in that range, 29.374 to 30.626. No matter which one of these I used, would you be comfortable in saying that his mileage is 29 or more? Would you agree that all these intervals are 29 or more? Would you also agree that you could say his mileage is less than 31? Would that be reasonable? You know, what do you get? Well, it's less than 31 mil, you could say for sure. Are we good? So let's show you a question, a little bit different way to show you the information. Try to make sure that the answers aren't there because they distract me. Here we go. And the data has been collected and tabulated. So here it is. A randomly selected sample of 12 students at a university were asked, how much did their textbook cost them? And here are all the numbers, right? So that poor person spent over $500 on the textbook in a semester. Ouch. Well, actually, now I look at it, didn't that person spend even more? Now, everything you need to know, including a 95% confidence interval, is here. So let's tell you what the numbers are. That is the mean, right? That's what you get if you added these all up and divided by 12. This is the standard deviation. It's the standard deviation of those 12 numbers. You imagine plugging them into TI-84 and getting the standard deviation. Now, the standard error is that number. You see it? Now, if you wanted to get the standard error, don't you take this number and divide it by the square root of that number? So I'm going to do that as a check. So the standard error of X bar, they're calling it SA mean, is 98.1. So 98.1 divided by the square root of n, which is 12. And the answer I get is 28.3 and stuff to one decimal place. That is exactly what they said it is. And they even go and tell you a 95% confidence interval. I mean, essentially, you've got nothing to do. Isn't everything, here it is, handed to you on a plate. Now, using the empirical rule to create an interval that estimates the 95%, right, of the individual students at the university, not the mean, round your answer to the nearest dollar. So let's see what they're on about here. Use the empirical rule to create an interval that estimates the textbook expenses of 98% of the individual students. Ah, not the mean. Sneaky. This guy here is using the mean plus or minus two of these guys. So far, so good. But we are going to do it with this fella plus or minus that guy. So when they say, where is the clue to that? Of the individual students, that means using only this data, not the standard one. Let's jump over and see what we get then. According to the empirical rule, right, just the generic version, isn't the answer the mean plus or minus two standard deviations? Right. Isn't that the generic empirical rule, right? A 95% confidence interval is this guy. The mean is 435.4. That is not going to be the standard error. That is actually just going to be the standard deviation. And so we're using that number. And so it's going to be 435.4 plus or minus two of these guys. Let's see what we get. 435.4, take away 196.2, gets me 239.2, and up to 435.4, add this guy. And this time we're going to get $631.6. That's a 95% confidence interval of the individual students. Now, let's do the other version, which is actually the most common one. Isn't this the 95% confidence interval of the sample? not of the individual students, but of the sample. And so we have a mean, which is still 435.4, plus or minus 2, but the standard error is 28.3.
Wait, so what was that first 95% of the?
This is the confidence interval of the individual students. And this is the confidence interval of the sample, right? So if you just looked at the individual students on their own, this is the confidence interval that shows you the kind of range that they paid. And this is the confidence interval of a sample, right? And so in this case, it's, let's double that, 6, 16, that's this guy. Well, actually, I know what the answer is. It's 373.1 to 497.7. That's the numbers that they want in question 6. They don't want this number. In fact, they gave you this number in the table. They only wanted this one. So the key here is a confidence interval of this individual students or a confidence interval of the sample, right? Now the formula look, I'd say almost identical, don't they? Isn't the only difference who you use for the standard deviation? If it's individual students, don't you just use the standard deviation? But if it's the sample, you use the standard error. So as long as you're quite sure about the difference between these two, you should be fine. Any questions about that? Okay, let's make up one. We're basically focusing on these questions. That was just a one-off. These are the main questions. So I collected the data on 500 students, and I found out that their mean IQ was 101, and that the standard that I got was 15. The standard deviation is 15. And I want to take from this sample, I want to predict an interval for the population IQ. Right, so this is OC students. I took 500 and their IQ was 101. Standard deviation I got from them is 15. And I'd like to know a 95% confidence interval, right, of this guy. So we are going to be doing a 95% confidence interval. So it's going to be the mean plus or minus 2 standard errors. And the standard error of the sample is its standard deviation divided by the square root of n, which is 15 divided by the square root of 500. So the standard error, it's a typical type of question, is going to be 15 divided by the square root of 500. It should be nice and small, yeah, 0.67 to 2 decimal places. So our 95% confidence interval is 101 plus or minus 2 of these guys. So that's 101, give or take that guy. So that's going to be 99.76 up to 102.24. So there's my interval. And I'm 95% confident that all students' IQs are somewhere in this range. So let's do some correct, wrong assumptions here. Using that interval, would it be reasonable to conclude that the IQ of college students is greater than 99? Would that be a correct assumption? Yeah. Would it be correct to say that their IQs are less than 105? Yeah. Would it be correct to say that their IQ was greater than 100?
No.
Well, you notice this one has numbers either side. And so it contains 100. So the answer is no, it's not correct, right? Couldn't this actually have an IQ of 99.5? Remember, every number in the interval is just as likely to be the true answer for all college students, right? The average of all of them. And so, nope, that one would be wrong. So you can make predictions about how big it might be, how small it might be, as long as you pick numbers that are not these guys, but a little bit bigger or a little bit less, that's going to work. But if I use any number inside here, isn't the answer B? No, you wobble. You might be right, you might be wrong, but you can't say for sure you're always right. Could the IQ be, just could it be 100? Yeah. Could the IQ be 102? Yeah. Aren't both of those just as likely as each other? But 100 is just as likely to be true as 102. Remember the rule that's true in every one of these intervals. Every single number in this range is just as likely to be true as any other number in this range. So let's do a quality assurance type question. What do I mean by that? Right. If you work in a factory that produces things, right? So we are going to pretend we're in a factory that produces boxes of cornflakes. And the boxes of cornflakes are 16-ounce boxes. I'm assuming you can get 16-ounce boxes of cornflakes, right? That's what they're advertised as. So from time to time, they randomly collect a batch of 100 boxes of cornflakes. And the average is 16.3 ounces. Now, the government has regulations like whenever you advertise that something weighs a certain amount, it kind of should weigh that amount. But they realize, that there's going to be a little wiggle room, right? You can't measure a box. Couldn't you put in a really, really accurate scale and say, well, it's only 15.999997 ounces. I'm suing you, right? The government doesn't expect that. So what the government says is if you say a box has got 16 in it, then on average, shouldn't it have at least 16 in it, right? Now, does that mean occasionally you'll get a 15.8 and 9? Yeah, but won't you also get a 16.4 or 5 as well? So that should average out. So that's the sample mean. And the standard deviation was 1 ounce. Let's do a 95% confidence interval and see if the cornflake manufacturer is going to be safe. Whether they can, say to the government authority, yeah, our average is good, and typically 95% of people will get a box well within that range. So let's see what we have. It's going to be the mean plus or minus 2 standard errors, because that's typically what we use. The standard error is S over square root of n. That's 1 over the square of 100, 1 over 10. I made my numbers nice and simple, 0.1. And so in this case, it's 16.3 plus or minus 2 standard errors. It's 16.3 plus or minus 0.2. And that gets me 16.1 to 16.5. Would the cornflake manufacturer company be safe now? The average box, would you agree that's bigger than 16 ounces? Right. Yeah, cool. You okay with that? Right. Now, let's suppose that 2 months later, they do another test and they measure the weight of 100 boxes of cornflakes, and the mean comes out as 16.1 and the standard deviation is 2. Now you might say, well, they're still okay, right? The average is still better than 16, so you're nothing to worry about. But let's see if that works with the standard that is imposed on them. And the standard imposed on them is that a 95% confidence interval must be bigger than 16. Would you agree this is bigger than 16? Everybody. Well, this time, we're going to have a standard error. And standard error is 2 over the square of 100, which is 0.2. So we are going to get a mean plus or minus 2 standard errors. The mean is a little bit lower, and the standard error is a little bit bigger. So we end up with a 15.7 up to a 16.5. Can you see that they're now in trouble? This sample had a mean of 16.1, but isn't the 95% confidence interval saying that your average could be anywhere in the range 15.7 pounds to 16.5, which means couldn't you be producing 15.7 boxes of cornflakes and 15.8 and also 15.9? Couldn't any of those three guys, couldn't they be possible answers? Agreed? Which means that weights and measures is what we call them in Britain. I don't know what the office is called in America. Anybody know off the top of their head what you call the people who go and check that, you know, if you say it's weighs this, then it really weighs that. Weights and measures are what we call them. Anybody know what it's called in America? There's a government office that's what they do, right? They go around factories and they check all sorts of things. So they don't just check that. They check cleanliness. They check, you know, how dangerous the working environment is, right? They do a whole lot of things, but that's one of the things they check. So this company would be in trouble.
No, it might be the Federal Trade Commission, but probably not.
Probably Commerce Department, some subsection of the Commerce Department then, right? But there's somebody who does this job. It's done in every country. So this company is in trouble. What they would have to do is stop it. Now, imagine that they fixed it, right? And they went into the machine and they turned the little knob so they put more cornflakes in, and they got this as their answer. Now they're totally safe. Would you agree the government's going to say, yep, you're definitely producing 16 ounces? Why would the company not like this?
It's they're producing more, but not enough to firmly say they have change it to say they have 17 per box.
Yeah, so aren't they just giving you free cornflakes? Because the box can only say it's got 16 ounces in it, right? But they're actually putting probably, you know, an extra half ounce in, or at least something like that, right? So this is quality control. You test things to make sure that they're within a certain accuracy, a certain reasonableness, and you don't want to give away free stuff, but you don't want to be caught here because you can get, well, you can all sorts of things. You can get fined. Do you know if they're really being awkward? Do you know what they could do? Couldn't they say, I want you to recall the last 100,000 boxes of cornflakes because they're underweight and you shouldn't be selling them? Can you imagine how much that would cost you, right? because once you bring the boxes back, you probably can't open them and rebox them because that's probably got health concerns, right? Not allowed to do that either. So they don't want to be caught out, but they don't want to, give away free stuff because that eats into their profit. What they want is an interval like that. Would you agree? That's bang on. Safe, but not giving away too much. Last name and bye-bye for today.